Okay, let's get started. This is lecture number 5, and today's topic is design patterns for object orientation as it relates to programming in Objective-C. This is really a theory lecture, not really a hands-on programming stuff. We've actually seen everything there is about the language so far, believe it or not. The language is pretty similar to C++, very similar to Objective-C. Well, I should say C++. Objective-C is similar to also Smalltalk. So the language syntax is just one component of it. So today's lecture is on the concept of design patterns and UML and where UML actually fits in. And then Objective-C makes it for a good language to discuss UML for. Because UML notation uses the pluses and the minus, which is what Smalltalk uses, which is what Objective-C uses in terms of their documentation of the objects in the class implementation of the objects. So it makes a little bit of sense. And also I want to talk about design patterns and Model-View-Controller as well. And then there's a Model-View-Controller example that I'm going to show you at the end if I have time. Otherwise we'll finish it up on Monday. But it's worth looking at only because it kind of shows you how the different pieces, in fact we might do it today actually in the iPhone class, how the different pieces of the program fit into either the model category, or the view category, or the controller category. So introduction to UML. In terms of what it is, patterns are two software design. So UML and patterns are two software design tools that can be used within context of object-oriented programming. UML is probably the most popular, actually. We have this thing called patterns, though, and design patterns as a concept. So UML is the graphical language used in designing and documenting object-oriented programs or software. So any language. So this, what I'm giving you today, applies towards any object-oriented programming language. So it's very, very general that way. So a pattern in programming is a kind of template or an outline of a software task. And we usually call those design patterns. Sometimes you get this information in software engineering courses because software engineers focus on design patterns when building the architecture for the software. But as a programmer, you have to be familiar with the programming design patterns as well so that you can implement them and make logical sense of what the information is that's being given to you. So pattern can be realized as different code and code in a different but similar applications. Most applications follow a particular pattern to them. Most Objective-C programs follow Model-View-Controller as their design pattern. So let me talk about UML first and the documentation, because this is kind of the way you can map out what you're going to implement before you implement it. And software engineers in general deal with the concept of unified modeling language. If you took my software engineering course, I jumped right into it without actually explaining how it relates to actual programming. So this is why I'm covering this information today. So we have pseudocode as a way of representing the program in a linear and algebraic manner. It's not UML, it's pseudocode, but the UML format for object orientation ends up being a form of pseudocode if you think about it. So it simplifies the design, eliminates the details of programming language syntax, takes all the syntax out of it. Graphical representation of the system may also be used. There's a lot of UML tools that work with Objective-C and out there. In fact, all of the naming conventions in most of the programs that you see in terms of book examples are following a UML kind of format. And then all of the naming conventions of all the default files in Objective-C for Xcode are following, because you always see view controller class, app delegate class, and all these different naming conventions. And it usually takes a while for students to kind of figure out what in the world are they talking about, all these little pieces. And the hardest part is, in the beginning, is figuring out, well, what goes in each file. And it depends on whether it's model, view, or controller in terms of that component, which is why I'm going to show you that. So unified modeling language is yet another graphical representation that's it's formalized, and it is designed to reflect and use the object-oriented philosophy. So a little bit of history of UML. It was actually around long before Java, long before C++, right around in the beginning of Objective-C and Smalltalk, actually. So it was actually made for this language, or a variation of this language, a Smalltalk language. So different groups have developed graphical representations of object-oriented design, starting with the Brock method. So usually you see Jacobson, Brock, I can't pronounce his name, but you see the books are written by these guys. Nobody else has written books on this stuff, or not too many. I shouldn't say nobody. Never say nobody. But these are the most popular one. The Brock method is probably one of the most popular because he's written the most and done a lot of the book and the documentation of the methodology. Its purpose is to produce standardized graphical representation language for object-oriented design documentation. Just meant for documentation purposes and also for design purposes. Since the beginning, however, it's warped a little bit. UML has developed and revised in response to feedback from the object-oriented community and developers. And today the standard is maintained and certified by the OMG, the Object Management Group. So when you hear about, usually in relationship to Java and C++, Objective-C, Corba, you hear about OMG because it's the object. It's not a standardization, by the way, it's an organization that's come together to set best practices and standards that people are following, to define what in the world object orientation is. Why do we care about any of this stuff? Is because if you don't actually have a methodology that you're using or a design pattern that you're applying towards the solution to the problem, you're pretty much just throwing darts out. And you're pretty much, flipping a coin to decide what classes you're going to make and how you're going to design the program. And what I want to show you actually is, and I'll show you, I'll just briefly show it to you later. I've taken the view concept that I broke, that adventure game that I've been playing with. I completely broke it and put all the views into one controller. And then I decided, well, that's really a bad example. So then I split it out. So now I have multiple view controllers with multiple views using a storyboard and one app delegate to keep track of the data, plus one class to keep track of the game, the statistics about the game and all that other stuff. So, and you can see how, if you look at it now, you go, wow, that's a much better application. It's a better application, less error prone, easier to organize. I don't know if you remember, I saw the little screens were piled on top of each other. I was like, which one goes first? And the overlaying and stuff like that. Well, it's just an experiment to prove the fact that, it's worth it to follow a design pattern because it makes the code easier to read, easier to modify. I didn't have any bugs in it originally. Well, actually, there was a lot of tweaking in terms of the order of the views and stuff. And it was a very non-standard implementation, but now as you'll see, it's very extendable. So if you do it correctly, it's not quite no tweaking at all, and you can extend, you can grow the application, and then other people can look at the application and understand what's going on with it as well. So, all right, so the UML class diagram is what you look at in terms of a programming perspective. There's other different types of diagrams out there. We're just looking at the class diagram. If you want a full, complete UML background, take a software engineering course. So, classes are central to the object-oriented program because of the implementation of the objects. So the class diagram is the easiest of the UML diagrams to represent and understand. And it's divided up into three sections. We have the top section that contains the class name, the middle section that contains the data specified for the class, and then the bottom section that contains the methods. And in terms of the specifications, the data specification for each piece of data in the UML consists of its name followed by a colon, followed by its type, and then each name is preceded by a character that specifies the access type. So it's really the specification file that you're building. In some of the UML tools, you press a button and it will actually produce the .h file for you, which is the specification, or the interface. In Objective-C they call it an interface. In C++ they call it a specification. So it's the same concept actually. Because in C++ you're supposed to build classes as well with a .h and a .c++ file. And so you have the specification and the implementation. In Objective-C we have the interface and the implementation. So we use a .m and a .h instead. But it's the same concept actually and follows through with object-oriented UML design patterns actually. Okay, so then we have the minus sign indicating it's private access. Well, that's the same thing actually. Private is within a class, within a method, within a class instance. So, or plus, which means it's public access outside of the class implementation, available to all objects. We don't have a sharp or tilde indicating protective classes or packages. Packages is more of a Java method. So we have a protected access. Well, we use a slightly different method for that actually, but the implementation is still the same. So this should be standard across all object-oriented programming languages essentially. So in terms of the diagrams, each method in the UML diagram is indicated by the name of the method, followed by parenthesis parameter list, a colon, and its return type. Sounds very small talk like. So the access type of each method is indicated in the same way as the data is, and we're going to see a diagram in a few minutes that puts it all together for you. The class diagram need not give a complete description of the class. It's not a documentation that's going to essentially give you pages and pages. It's supposed to be a picture and a quick look. So if given analysis does not require all of the class members to be represented either, for those members that are not listed in the class diagram, missing members are indicated with an ellipse or 3 dots, meaning it continues, like dot, dot, dot. So here's an example here. In fact, down here we see square with dot, 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 meaning that it continues. So this is a rectangle, kind of. It could be a square, it could be any sort of box structure. The name of the class square is on the top. And then we see the notation minus side, colon double. Very small talk, very Objective-C-like. So this is kind of just, it's kind of like, just an indication that UML is like a really nice documentation language for these languages, actually, for both Smalltalk and Objective-C. Because the syntax is following through, and those pluses and minuses actually mean something. And in C++ they don't, because we don't have C++, we don't actually have pluses and minuses that we put on method calls that indicate whether or not it's publicly available or whether it's private inside of a class object. So minus would say that these sides are inside a square. In fact, all of these are minuses because they're all going to be inside of this class object. Square. So we have an x-coordinate and y-coordinate. Well, the colon is that it's not necessarily the same standard as the method call, and these are not method prototypes, by the way. These are just the notation that's used. But I thought I'd show you that the notation is very similar to Objective-C notation. So most people that come from a C++ background, they go, well, they want to see the opening and closing brackets, and they want to see, no colons. They want to see commas in between stuff, and it's a slightly different kind of thinking, which is kind of interesting, actually. So these are the data members. These are the member functions. Member functions, we switch it around. This is more UML notation versus Objective-C, where the data type's at the end. But it's the same concept. And these are pluses, which means they're available outside. They're public. They're publicly available outside. Which means if you implemented this in Objective-C, you'd be pulling these and probably making these into private inside of the class. Excuse me, these are public methods inside of the class. But you're not going to be using a plus, you're going to be using a minus because of where you're locating it. Method is going to be used inside of the class. So the indentation in here is in a different context. In terms of the class object of the diagram, the plus means that these are public and the minus means that these are private data members. In terms of which is the same meaning of those symbols, but different contexts inside of the actual implementation. This is not giving you the source code. This is pseudocode. It's giving you the documentation for it. Erase, and we can see that erase actually is notated by the. I had in the previous slide. I had the symbols here. Here we go. Indicates a protected across access. So protected method versus a package accessed. So we don't have any package accessed methods in here, but this one is protected erase, which means it's not publicly available. It's protected. And then we have the class interactions to consider, and this is what you're considering when you're designing programs, either for the iPhone or for the Mac, or for whatever platform, whatever way you're designing anything for. We always have to think about the interactions. And so that rather than showing just the interface of the class diagram is primarily designed to show the interaction among the classes, which are the messages that are being sent back and forth. So this is where that term message comes into place, especially for Objective-C, because these objects are sending messages back and forth, and then that's their interaction. In other languages we call them methods or functions, but it's kind of the same concept as well. So it's just different terminology. So UML has various ways to indicate the information flow from one class to another using different types and sorts of notations and arrows. And so it has annotations for class groupings into packages, for inheritance, and for other interactions as well. In addition to establishing the annotations, UML is also extendable. So we can add new symbols to it and basically modify the diagrams for the language that we're using to indicate certain things about the implementation that may not necessarily be obvious. So we also have inheritance diagrams, which are kind of like the most important or the critical part. Is the class diagram, you have to have the basic notion of, which objects are you going to create for your program. And then the inheritance is more along the lines of, well, which object is going to extend from which other object, and how we're going to line up the hierarchy. So the UML diagramming technique is actually supposed to help you develop the hierarchy by having you graphically look at it and go, well, that's the logical order, and see where the relationships come into play. And then you can see if one class is interacting a lot with a bunch of other classes, then maybe that class has got the wrong identity. Like there's not equal interaction among all of the classes, just one class is doing all the work. Then you're probably having something wrong with your design. You want to have like equal spread across all classes, having them do about the same amount of work. You're going to have some stronger classes in there for the most part, at least one or two probably. But the object is to spread it out. So an inheritance diagram shows the relationship between the base classes and its derived classes. Normally only as much as the class diagram is shown as is needed, which means you're not going to show the whole thing. You're only going to show what's needed important to grasp the concept. There might be some smaller, less significant classes that get added into the design later on. It's not like a set-in-stone document. So also note that each derived class may serve as a base class for a derived class as well. And each base class is drawn above its derived classes. So we put the base class above the derived classes. So the hierarchy goes the upside down. So an upward arrow is drawn between them and to indicate the inheritance relationship. So here's our relationship with inheritance. In UML, you're actually supposed to draw the arrows up because you actually are going up. So person would be the base class, and arrows are from the class to the base class. And so from person, and this is basically the example that we saw in class actually, student and employee, and employee, well, we have staff and faculty, and the students can be undergraduate and graduate. And you can sort of build this sort of like a representation of your program, and then take this and just create an interface file for each one of them, and you know exactly which one comes from which one. Actually, person comes from object, so or NS object, and it pretty much takes all your work out of the way. So other classes, not mine, but other classes will have you actually write these diagrams for your programs. I actually thought about doing that actually. It would be kind of easy if you think about it. It's kind of like a lot of exercise work though. It's kind of like a lot of paperwork. But you remember in the old days people used to write flow charts and stuff for procedural languages, for BASIC and stuff. You wrote a flow chart and stuff. This is the equivalent to the flow chart. This is mapping out what you're going to implement before you implement it. So the assignments themselves actually lend themselves to really easy, just like this, kind of diagrams. Where we have a ship, and we have a cargo ship, and a cruise ship. We have a, or we have well, the parking ticket meter program. It's going to look slightly different. There's not very much of a hierarchy to that. Instead, you're going to see single lines of inheritance. And then the purpose of those assignments, well, one of the purposes of the assignments was to actually kind of bring to light how the hierarchies should be created and the different varieties of hierarchies that exist. And the fact that, you might have to use a class inside of another class for which you're not inheriting from. As an example is going to be that adventure game when I show you the finished version of it where, we're making an instance of the game class. Or we're calling, we're going at class, game class, but we're not inheriting from it, we're not doing anything, we're just using it. Or maybe we're building on it. Like you missed the protocol examples actually. We did protocols and categories. The last class, if you watch the videos on protocols and categories, implementations. So anyway, so some teachers actually require you to write these things out for each one of your programming assignments, because then saves you time and energy actually, because if you pre-plan the hierarchy, then but I'm giving you the hierarchy, so it doesn't really make any sense. But if you write it out, it might actually help you visualize what you're supposed to be implementing. And then it also helps you figure out, well, what belongs in each one of the classes. Because what you want is your data to be logically organized as well as the functionality on the data. In terms of, because we haven't started talking about design patterns yet. Right now we're just talking about UML in terms of the object structure. which kind of is, this is going to separate a good programmer from a bad one. Someone who has really good design skills is worth a lot more, actually, because they're going to make something that doesn't look like spaghetti code. You know, the really bad designer is going to put everything all in one class, not use a view controller, not think about any data model. It's just going to make something that's really hard to maintain, hard to grow. So if you follow the design patterns and the structure of the hierarchy correctly, that generally lends to a longer living application and a more well-structured one, and then one that can be documented correctly. See, this is beautiful. I've had students do applications very similar to this, where the student was the person and the person was the, you know, like they had a student and they had something coming from it, and it was both the student and it was also an employee at the same time. You know, it had all that stuff in there. Or they put it all into one. Put everything into one, and then you got a person who's a staff and an undergraduate all at the same time. And it's just confusing. So this is a little bit easier, actually, now that you've been staring at it for a while. So it's a little easier to conceptualize. So inheritance diagrams, the arrows also help in locating method definitions and where the method should actually be, where the method should reside, and what messages are going to be sent back and forth. Because the person's going to need to know, from a message perspective, the employee is going to get the person's name, age, anything about the person is going to come from here. And the staff might have to get the employee ID, might have to set the employee ID. So the communication is actually kind of interesting when you look at it in terms of the hierarchy. So it's going to definitely tell you the definitions of the methods and where the methods should actually go. So you look for a method definition for a class. Examine the class definition first and say, well, what is this class? It's a person. And then if the method is not found, the path for connecting the arrows will show the order of the direction in which to search for the method. So if you're down here and you want employee ID, well, that's going to be an easy one. You're going to come to employee. But if you're, let's say you want the person's name, that's probably not going to be until you get up to here. So it kind of helps you in terms of the hierarchy to figure out where that information is going to be stored. So you examine the parent class indicating the connection arrow. So if the method is still not found, then you examine the parent's class and you work up the hierarchy until everything is found. And then you loop to the base class. And if you reach the base class and you know that you're missing that piece of information, then you just say, well, where does it belong? And then you can logically place it. So it's kind of like, you know how people organize their desks or their file cabinets or their bills and payments and stuff? You know, some people just put everything all in one file, and some people separate it out into different folders. And then some people make duplicate employee folders, which that's overkill. You can get to a certain point where you've got too many classes and you need to start condensing things down. So here's some details of the UML class hierarchy that can also be indicated. So person here, we know it's going to be a private data member here, name, and it's going to be a string, or NS string in our case. And we're going to have a set name, a get name. Well, these are the, you know, this is where this all comes from. So if we use the property and the synthesize, we don't have to put the get and the sets in here for our language. Other languages, you actually have to write it, which is why people would just standard, you know, one set for each one of the data members and put the data type next to it so we know what it's supposed to be, because this data type has to match this data type. And then, you know, this is obviously going to be this method is going to be void, this one's going to be a boolean to come back in true and false. Is it the same person? To compare a person with a person kind of thing. And then the student number, which is going to be an integer in this case, and then we can go through, and we have, you know, is this student equal to that student? Is there an equals? There's a toString method. And then that's where we can apply protocols to these. So if you remember last time, the protocol is one of these interfaces. If you put a protocol, and just kind of bring in last week's lecture with this week's lecture, or Mondays with Wednesdays, if you apply a protocol, and a protocol is a single interface that doesn't belong to a class, it's outside of the class, and you apply the protocol to the object, then you know that each one of these objects is going to follow the same rules. In Java, we call these things interfaces. Implemented interface this, implement, comma that. And we could mark it because protocols can actually have, you know, IDs and things that are trackable. If something belongs to a protocol, it's equal to another object that does. But in the case of this particular example, the protocol would ensure that we had a toString method, for example, for every one of the classes that was in this hierarchy. If they all have to follow the same protocol, and we put everything in the protocol that we want these standard classes to include. And then in the UML notation, we actually have a notation for a protocol or for an interface. So we can define that out as well, which turns into another diagram. So that was your UML exercise. That's pretty much all you need to know about UML. From a programmer's perspective, what you're doing is you're filling out these class boxes. So UML is not that hard, is it? That's it right there. You're looking at the UML diagram. Well, you're looking at the shell of one filled in. It looks like that for each one of the objects. If you had that, then you could go over to your computer and start typing everything in, essentially, and you'd be essentially. And then, or if you use one of those rational rows tools, I think it used to be called rational rows. I think it's changed names now. I think ObjectShare also used to make one that worked with Smalltalk. That worked with, that also worked. I believe it worked with Objective-C, but don't quote me on that, where you just pressed a button after you built this, and it gave you the interface files in the format that they were supposed to be in. And you just took those files. In fact, maybe that's going to be a future addition to Xcode, who knows. It just took those files and you just implemented it. You just wrote the implementations. Because what are you doing with this anyway? You're creating the interface to the class, the public and the private interface, and the protected interface. And you're just, when you're programming, you're just writing the implementation. The M's for all this, the .M's. So let's talk about the second half for today, the patterns, design patterns and patterns in general. We're going to look at the Model-View-Controller in a little bit more detail to see how the design fits with object orientation, because there's a missing link that most people don't actually see until they start trying to rate applications, and you're like, well, how in the world is this thing supposed to come together? When do I want to use a view controller? You know, when do I want to use it? What is a view anyway? And you know what? Anyway, so the patterns are the design outlines that apply across a variety of different software applications. All software applications follow through, and I'm going to show you more than just Model-View-Controller, just to give you some examples, but I'll kind of skip through those. But it's the pattern, the structure of the form that you're following. All iPhone, iPad applications follow Model-View-Controller, every single one of them. Now, whether or not the programmer knows how to program with that design pattern and use it correctly, as you've seen with my adventure game, I broke the rules completely, didn't follow Model-View-Controller. And then I decided, well, if I'm going to finish this, it's a nightmare. I had to put it back, so I put it in Model-View-Controller, and we'll see. I'll show you Model-View-Controller. So remind me, actually catch me at 6:25 or 6:20, so I can at least have 10 minutes to show you that. But anyway, what are we looking at then? So to be useful, a pattern must apply across a variety of different situations, and to be substantial, a pattern must make some assumptions about the domain of the applications in which it applies. So we're making some assumptions, we're applying stuff, you know, with some sort of a generic kind of pattern. And some of the most common patterns outside of, let's say, Model-View-Controller, which is popular for object orientation. The other patterns fall in the category of data structures and algorithms, actually. We have only a limited number or set of known algorithms that do sorting, that do searching, that do problem solving in general. And when you're writing a program, one of the things you're thinking about, is not only the model of the program, but also what data structures you're going to put in there, what algorithms are you going to apply to it. And what you're going to do is, and whether you know it or not, you're going to go back and start using some design patterns. And those are patterns that are essentially well-known things that people just put together. Well, they've been studied. Best practices, call them best practices, if anything, that work. So the Container-Iterator Pattern, and I showed this to you, I believe, in the Java course for those people who took that class. And it applies actually towards everything else beyond Java as well. But the Container-Iterator Pattern, the container is a class or other construct whose objects hold multiple pieces of data. So we have the concept of the container, and then we have the concept of the iterator that works with the container to sort the container. So as a data structure, or even as a, you might consider the iterator more of an algorithm / data structure. The container is a pure data structure sometimes, but you're looking at how the objects are working with each other. classic example where you have to think about this is going to be in the parking ticket program. You have an object that's a car that's parked at a meter. You have an object that's a police officer, not inherited by car, and please don't inherit police officer from car. And then you have a meter, parking meter. Well, these are all separate objects that are going to have to work together. So you're going to have to come up with a pattern. It may not necessarily be a container iterator, but you're probably going to use an iterator, and you're probably going to have a container in concept, because you're going to have something to keep track of how long the car's been sitting there, how many cars have been sitting there, maybe, I don't know, I can't remember, but there's information about the car. There's information about the information that needs to go on the ticket, because the object that's writing the ticket, and the ticket's another object. The police officer is not the ticket. He's the police officer. The parking meter guy is the officer. I'll call him an officer so I'm consistent here. He needs to get certain data from the parking ticket component, who needs to get certain information from the meter component, who needs to get certain information from the car component. So, long story short, you got communication between these objects, not anything having to do with inheritance. And it'll be interesting to see how you guys implement it, because there's multiple different ways of doing it. If you follow a Container-Iterator Pattern, you can utilize well-known, this is just one pattern, by the way, I'm going to show you a bunch of other ones, but this is just one way of sort of visualizing scenarios. Usually in this particular, we have a list, or we have a container, or a box, or a bag, or something of something, and we're sorting it in terms of this model. So it might be an array. So an array is a container, a vector is linked lists or containers. A string value can be viewed as a container that contains characters and strings, actually. In fact, we used a container object in the string reversal. Was it this class? String reversal program? No, actually it was. It was the category did the string reversal from Monday. It wasn't that long ago. I don't know why I don't remember it. Any construct that can be used to cycle through all of the items in a container is called an iterator. So it's a design pattern that's associated with cycling through iteration, through containers, or through lists, or through other structures. So an array index is an iterator for an array. So, and that's why the index concept is part of the array in terms of its implementation. So container-iterator patterns describe how an iterator is used on a container. So now we have an adapter pattern. Adaptor pattern transforms one class into a different class without changing the underlying class, but by merely adding a new interface to the class. So we adapt a class. Well, what does that sound like? The use of protocols is an adapter pattern. We take and we apply a class and we apply a protocol in the class, and then we implement the methods of the protocol. Think of a protocol as an interface that we're implementing. If we take a student and we adapt them into a graduate student, that's an adapter pattern. So it's anything of taking, let's say, in this particular example, for example, one way to create a stack data structure is to start with an array, then add a stack interface to it, which is actually what we did in the data structures course. And most people did it in Java. And you can implement a linked list, which is a list, and adapt the linked list into, let's say, a stack or a queue or anything. It's really referred to as an adapter pattern. So it's a design pattern, actually. You're building structures from other structures and you're adapting. Well, you can do the same thing in object orientation. You can adapt a person into an employee through inheritance, but you can also adapt them in other ways too. You can transform the object without changing the object, essentially, without rewriting the object. So that's really referred to as adaptation or adapter. And then we have Model-View-Controller Pattern. Alright, this is the one that is most particularly of importance because it's the one that the iPhone, iPad development uses. iOS uses it. And so does that, believe it or not, Coca applications. So the pattern is a way of separating out the I/O tasks from an application from the rest of the program. So the I/O from the logic from the data of the application. So the model part of the pattern performs the heart of the application. Well, what's the heart of all applications? Data. So some people call that the data model. They call it the model, which is really the data, the storage. And where we have things like classes. So in a regular building of a COCA application, you're going to implement the data, and I'm going to, let's say, work with that adventure game I was talking about. Well, I'm going to actually make a game class. And the game class is going to represent my model. It's the model of the game. It's all the rules of the game. Everything associated with how people get health points and lose health points and everything associated. It's going to be part of the data model. It really belongs in a separate object. It shouldn't be mixed in with the view. It shouldn't be mixed in with the controller. It shouldn't be mixed in with anything outside of the data. So the view part is the displays or the outputs, a picture of the model state. So the views, they are actually called views. We drag and drop a view and we stick it in a window. If we don't do that, we have a default view that we work with. And the view is given for us. So the view is the visual representation of the data. So in the view, I was sticking the data. Because I was taking, the view, you clicked on this item and then there was a temporary piece of memory being held. Well, the problem with that is that each view resets itself for its view. And there's no view communication. You communicate views, you can pass information back and forth between views, that's okay. But the model part of it shouldn't be kept in the views, only because then you're not going to be able to keep track of that data. It's going to be all over the place. In my example, it was like in 7 different views, and it was all over the place and wasn't not very organized. And plus, you don't really have persistent storage of that. It's going to be garbage collected when it's no longer in focus. It's going to be released. The view's gone, so is all the data associated with the view. So you're going to have problems, and if you go online and you go on the internet and you search on, how do you transfer data between views and stuff like that, and you say so many people are going down the wrong track, and they're trying to make the wrong design pattern work for them, and you'll bang your head against the wall for days on that one. You might work a fix out for it, but it takes you twice as long to write the application than it does just to follow through. Put the data in it. If you're not going to use a class, put in the app delegate. And have the app delegate make an instance of an object for you. And then take that instance of the object and use it in your view components. Well, we're going to use it. Probably not going to use it in the view. You're going to use it in the view controllers, which is the third part, the controller. This is the input part. It relays commands from the user to the model. So the controller is the interface between the view and the data model. So it's the reactor and it's what's holding the IB outlets, the IB actions, all of the different things that are going to be performed from the IB, which is the interface. IB stands for Interface Builder. So it's taking the action and performing something on it. It should be taking this instance of the object that was created from the data model and changing a value of a variable, or it should be updating a value, or I don't know, doing whatever it's supposed to be doing to get the application to work. So that's actually how you're supposed to build the applications. You don't actually have to do that. For example, if you're just going to build an application that holds up a website, you don't have to know anything about Model-View-Controller. Because you just pull out the first view you see, you drag a web view component, you stick it in there, and you assign it to a URL, and voila, your application's done. So you might think that Model-View-Controller, and you'll be correct if you think this way, is for larger projects. It's for the big, full applications. So to build small apps, no problem. To build a big one, yeah. I don't know what it is about this room. My allergies have been going crazy. The longer I stand in this room, the more congested I'm getting. I think I'm allergic to ITU. Alright, so the Model-View-Controller pattern, each of the 3 interacting parts is normally realized as an object with responsibilities of its own tasks. So we actually have 3 separate objects. What are objects? Are classes, which is why we have a view controller class, and we have app delegate classes, and we have classes, like other classes that we can create, and we can have XIB files or interface builder files for any of those classes, and then we can assign controllers to classes and say, well, this view here is going to be controlled by that view controller, and we switch the classes around and make sure that the class is controlling. It's usually one class per view. So we don't normally take multiple controllers for the same view. A little bit harder to do it that way. You can do it. You can make anything work, actually, but you're not following the model correctly if you're doing it that way. So each of the three components realizes that the object has different responsibilities for each one of the components. Model-View-Control pattern is an example of the divide and conquer strategy. And one big task is divided into three smaller tasks as well-defined responsibilities. So we just take the big problem and we break it down into a smaller one. As an example, the model might be a container class, such as an array. So bringing it back to the container concept. And so the model is going to be the container, which is going to be the data. You know, it's the whatever it is we're going to be holding all these numbers and integers or whatever for. The view might display one element of the array, so it just shows it to the user. Here's item number 1, here's item number 2. And then the controller would give the commands to display the element at a specific index. So the controller is going to go in and say, hey, give me number 5. So in this particular case, the controller would pop something off a stack, would put something on a stack. The stack would be in the data model, and the view would be showing to the user, you know, what items on top of the stack, or the visual representation of the data in terms of its current state or wherever you happen to be in the stack. So the model would notify the view to display a new element whenever the array contents changed or a different index location was given, perhaps. So the model would basically go to the view and say, hey, update me, or, you know, update your display, I've changed. So that's how you can sort of get all three of the components to work together. So in the game, you know, we have the view is just going to show the user the nice little pictures and the buttons. And then the controller, when the user clicks on the button, it's going to say, hey, they want to go into the jungle. And then the data model is going to be that model is going to say, hey, in the game class instance that you've created in that object that represents the game, go into the jungle. And then when you go into the jungle in the game, it's going to set your health score to something. It's going to improve your health score because you're supposed to go into the jungle. So, yeah, if you remember the game. So, an application can be made to fit the Model-View-Controller pattern, but it is particularly well suited for GUI user interface design projects. Any application can actually be put in there, but you have to have the view in order to make it worthwhile. So naturally, this is why devices, like, you know, iOS devices fall into, it's all GUI. Isn't it all about the GUI? Computer programs fall into this category. And actually there's design books for Android as well to follow through the same concept. In fact, Android is also Model-View-Controller designed, but it's not strictly enforced. It's not as easy to see it as it is in the iPhone development or in the iOS. So the view can then be visualized as the state of the model in terms of the concept. So here's a Model-View-Controller pattern where we have a model that notifies, and the model is the data, and the data is data item number 1, 2, 3, in the container that we have as our example. Notifies the view, update, somebody added something to me, and the controller added some item to the stack, or took some item away from the stack or something. So the controller doesn't work with the view. So people go, well, it's called a view controller. It's controlling the view through the model. So it controls the view through the model. So this is stuff you're going to want to know, because most people at this point start asking me, well, what's going to be on the final exam for this course? I never ask any programming questions. I will definitely have questions about Model-View-Controller, though. This is lecture number 5, by the way. And design patterns. And, you know, what are you doing with this iOS application? What's the view controller for? You know, what's this component? What's the app? You know, what does this do? What does that do? So, all right. So that's kind of, and I have the second part of this. I have more, but I'm going to take a break from model view for a second and look at some other patterns to reinforce the pattern concept. Then I'm going to go back, show you a little bit more about the model view in a few minutes. But a sorting pattern. This is where most people think, oh, it's just algorithms, sorting algorithms, you know, selection sort, insertion sort, binary sort, searching, sorting, you know. They're really patterns. So the most efficient sorting algorithms all seem to follow a divide and conquer strategy. So sorting algorithms, or patterns I should say, it's the strategy that defines the implementation of the algorithm. Because usually when you take an algorithm data structures course, most students go, well, how are you supposed to implement that? Or they think the efficiency of the algorithm is dependent upon their implementation. Well, it has nothing to do with it. It's the pattern of the algorithm that determines its efficiency. It has nothing to do with what language you implemented it in, or how you actually did it, what structure you used for it, or anything. It's the design pattern that gives you the efficiency for it. So as an example, given an array A and use the operator less than operator, these sorting algorithms could exist, and one of them is divide the list of elements and sort them into two smaller lists. Well, that's using a split. So as a design pattern, you take the big list of stuff and you make it into smaller lists. Well, that's actually kind of the binary sort of concept, but you have to take a sorted list in order to do that. But it's a design pattern. Or there's a recursively sort the smaller list with a sort, and then recombine the two sorted lists and join them to obtain the final sorted list to source them. So the method for the split rearranges the elements in the internal A begin through AN and divides and rearranges the level of the split point. Don't worry about the syntax here, it's just the concept that's being described. Two smaller intervals are then sorted by recursive calls to the method sort. And then after the sort actually occurs, then the method join combines them together. Okay, don't worry about it, don't have to understand. I'm not going to ask any questions on sorting. But the concept is that there's a design associated with it. If I wanted to be sadistic, I could say, tell me the design pattern associated with using a queue. And then if I were an answer, actually it's not on the slide because I'm talking about sorting right now. What's the design pattern of using a queue? Well, you have to have a data store. You have to have a container, right? And then you have methods that are on the containers. And the methods on the containers are making sure that the last people who enter in are the last people who are coming out of it. And that there's a functionality for testing to see if the queue is empty or if the queue is full. Or there's ways of putting things into the queue, and there's ways of taking stuff out of the queue. What I'm describing is the design pattern of the implementation of the queue concept, which is what this is describing for the implementation of a sorting pattern. And here's a merge sort. So don't be particularly interested in knowing what the sorts are. It's the pattern concept that you're supposed to be getting out of this. So simplest rationale for a sorting pattern is a merge sort, which is a different pattern, doing different things. It's describing a definition of a split. It's taking the definition of a join. It's more complicated. There's trade-offs between the complexities and the methods, so it's going to either be quicker or slower. And then we have this whole concept of the join and the join method. How are we going to put something together? Well, then that's going to be determining the pattern of the technique that you're going to use. So a merge starts by comparing the smallest element with the smallest sorted interval. The smallest of these elements is the smallest element of the subinterval, and the method for the join makes use of the temporary array, perhaps. The process is repeated on all of the remaining elements. Well, there's a methodology to it. There's a pattern associated, and all of joins are done the same way. Actually, all quick sorts are done the same way. All sorts, every one of these algorithms, it's implemented the same way. It's not the source code writing that's giving you the implementation. It's the design pattern that you're using to implement it. The pattern defines the method that you're using in terms of the implementation. Here's a quick sort. And I'm not going to go through this, but it's a quick sort algorithm. So you can download and go through it. And then we have restrictions on sorting patterns. Yeah. So like all patterns, the sorting patterns have some restrictions on where it applies. Well, there's restrictions on Model-View-Controller as well. If there's no GUI, it's really hard to implement it. It lends itself really well to GUI programs, where the primary focus is on the view, because it starts with the view. It takes the view and transforms it through the controller into the data model. So there's no view. Or if there's no data, in the case of the other example I gave you a few minutes ago with the website, if you're building an app to show a website, there's no data. Why do you have to use a Model-View-Controller? Don't bother. It's perfectly correct not to use it because there's no, it doesn't apply. There's a restriction that says, yeah, we don't have any data. We have a view and we have a controller, but we have no data. Everything's on the internet. It's just a front end of the internet.
So the view will be only for the IO application, not for the Mac application. So
the same concept applies to the Mac. We have a view on a Mac. We have a screen, a window. On a Coca Touch, it shows up as a window on an IO device. On a Coca, it shows up on your computer.
Okay.
Were you here the day we built the calculator? It was a window app. It shows up on the desktop. It doesn't run on an iPhone. Or on an iPad. It's kind of like Windows. You can use Model-View-Controller with Visual Studio to create Windows applications. I've actually, believe it or not, well, no, I shouldn't say that. I'm seeing it more and more now. Older versions of development tools from Microsoft never focused anything on Model-View-Controller. Because they say, oh, it's an object-oriented thing. An object-oriented thing kind of came from object-oriented languages that didn't work on Windows. Like Smalltalk. Or like, well, I don't know, Smalltalk does work on Windows now, but originally it was a Mac. It was Apple-oriented. Actually, I shouldn't say Apple. It was before Apple. But long story short, Windows itself has the same model. You can create a window motif using MFC tools, and used to be resource builders in there, where you can, I don't know what they're called because I haven't used Windows in years, but you can build a GUI, and then you can build a data model, and you can build a controller to it. And not as broken out as it is with Xcode, however. Not as obvious in terms of the implementation. But the same concept applies. But you have to have a GUI. So let's say sorting patterns have some restrictions also. So it applies only to types for which its less than operator is defined. How can you sort a list when you don't know which one is smaller or greater than another one? Impossible. So that's not a sort. So the pattern only applies when there's an order implied. And it applies only to sorting in increasing order. It doesn't normally take into the pattern doesn't traditionally take into consideration decreasing versus increasing order, because traditionally we're checking to see if something is bigger than another, or increasing it. And the pattern can be made more general, so the smaller than operator can be replaced with a Boolean method called a compare. We see this? We actually saw this in some of the Java examples if you were in the data structures course. So the compare method would take two arguments, base type of the array, and then return true or false if the comparisons were equal. And if they were, it could throw them into a container or something. So the efficiency of sorting patterns, the most efficient implementation of the sorting pattern are those for the split method, actually, because of the design pattern lends itself to a more efficient design. Divides the array into two substantial sized chunks, because if you follow all of the theory on algorithms, it's basically making the search space half of what it used to be. Smaller search space, obviously, is going to be more efficient. If I only have 2 items to deal with, I can find it easily. Versus 4, versus 8. And then the merge sort split divides the array into 2 roughly equal parts. The quick may or may not divide them into equal parts. So when it doesn't, worst case running time is not as fast as the merge sort time. So because it could be worse. Because you're playing around with the sort space, you might actually only take 1 item off. Have you really saved yourself very much time? Because you haven't divided the list very much. So efficiency of the sorting pattern, the selection sort algorithm divides the array into 2 pieces, one of the single element, one of the rest of the array element intervals. Because of the uneven division of the list, the selection sort has a poor running time to it. However, it's simple. So there's simplicity to patterns. I actually kind of think that most design patterns are kind of simple in context. You can get kind of complicated though, in terms of choices between all the different algorithms that you can implement. Some of them are easier to program than other ones. So the pattern itself just lends itself to a clearer design. So pragmatics and patterns. So the patterns are guidelines, not requirements. So they're guidelines. So it's not necessary to follow the fine details of the guideline, which is where you can see, as I said earlier, you can tell a good design from a bad design is usually, are they following a pattern? Are they using a design pattern? Or are they just throwing darts and they're just putting stuff in there? Hey, look, it works. Okay, but it's not going to work for long. But in some cases, they're guidelines. A lot of people don't like the guidelines. In fact, I don't like using data for some reason. I find that I like the view. The view and the controllers definitely are a must. I like to mix the data in. Or I like to use a database, or I don't like to work with the data component of it for some reason. And it's just maybe my own personal preference. But I think that's pretty common actually from a lot of the things I've seen people write. It's like the data is always like let's just mix it in. Why do we have to separate it out? It seems like there's more work to it. Only problem is, it's less work to mix it in, but then it's more work to fix it because it's not going to work right eventually. So. And we'll see my calculator. I have a calculator that's broken, actually. And I have one that's fixed, that's done correctly. So I was just playing around with it to put some examples together. Probably won't see it till Wednesday, though. Monday, I mean. So. Alright, so a little bit more history on the Model-View-Controller concept, just to fill in the blanks. That's what I was promising you before. There's just a couple more slides at the end here about how it relates to iPhone and Objective-C and that stuff. Framework pattern is reusable for applications, depends on the observer pattern. The observer pattern is view controlled, which the observer pattern was the original one before Model-View-Controller, actually. First developed by Xerox PARC for Smalltalk. Well, we're working with a language that was developed from Smalltalk, so it's definitely up the right alley. Used by the Application Kit system for Next Step, which is our environment that we're working with, the Coca interface, used by Coca APIs and the Apple OS X. So the entire operating system is actually implemented using this design pattern as well, because it's written with the same kind of things. Recommended structure pattern in Java, not strongly enforced, not something where you're gonna be required to, in your tools. There's nothing in Eclipse that's going to require you. In fact, there's a little bit in the Android SDK that kind of, the XML files or your views, that's kind of obvious. But your controller, concept's completely missed. You have to actually create your own controllers. And who's going to create their own controller? They're going to mix the controller in with the data, and they're going to have a view with data, and which is what you get in Android. You get an XML file with a class that works with the XML file, which is how people transform into iOS, and they do the same thing, which you can do. There's no right and wrong to it. It's just some patterns are better. So what's this observer pattern? Model-View-Controller is based on the observer pattern. Defines a one-to-many dependency between objects so that when one object changes state, all of its dependent objects are notified and updated automatically. So that's where this delegate comes into place. The delegate can keep track. So you can make an instance of an object in a delegate, or you can use the delegate to delegate changes that are occurring between the view and the model through the controller. So you can have a controller, a view, a class object, and an app delegate running. So you got 4 instead of 3 now. Or you can just get rid of the data model and use the app delegate for it. Or you cannot use the app delegate. You don't have to use the app delegate. You have classes in there that just sit in there. So when you make a default project, you get essentially these things, these objects that get created automatically that just sit around. For the iOS. For the non-iOS, you don't get a delegate. At least I haven't checked in a long time, but you never used to get one in the old days. In fact, I could probably just build a sample project when I'm all done just to test that out. But it's used to decouple the subject from the observer, since the subject needs little information to notify the observer, so it can result in excessive notifications. Yeah, they get a lot of talking going on. So if you're using all 4 components, you got a lot of communication that's going on between all the different classes. Do you really need that? It's kind of like putting a traffic guard out on a signal that works. If the signal is working, why do you need a traffic guard out there to direct traffic? You don't. So you get rid of that guy, and the system runs faster. So depending upon how you control the model, there's some bad things that you can do to it to make it run slower. One thing is to put in extra messages that are not needed, or extra stuff. So here's the observer class diagram, where we have the the thing to be observed, the observable, with the observer, person observing it, updater, with the account view, which is the view component, the summary view component, and then we have the data over here, the bank account. So the bank account might have an add observer, delete, notify observer, has changed, set change kind of thing going on, withdraw deposits, the balance, the get balance is going to be in this kind of functionality. And then the update, this view, update that view, and then, oh look, an update occurred. So the observer is just looking and say, hey, there's an update. Go notify the view, or go notify, take a look here and observe that there's an update, and then run the appropriate methods on the different classes to perform that. And then we have transactions happen. And here's kind of the typical way the pieces fit together for a banking application as an example. When you click something on the view, you're going to get the controller. The controller is going to say, hey, deposit, all right, into the bank account. And then the bank account is going to set a change. A deposit was made. It has to update the view. It's going to update the summary view eventually. But it's going to notify the observer. The observer is going to do the update on the account view and go back to the balance, and then update the summary view, go back and get the balance. It's basically the observer is coming in and saying, okay, let me keep track of all the views that need to be updated and all the information that needs to be communicated to. And when a change occurs, I'm going to go ahead and update all those extra views. So we have the concept of the controller, or the observer. So where I'm getting, the bottom line, what I'm getting to here, is we have things like controllers, and then we have controllers of the controllers, navigational devices. We have navigational approaches, and we've seen it already actually a couple weeks. No, we didn't see it in this class. We've seen it in the in the iPhone class, the tab view controller. And we have a controller number 1, a controller number 2, and then we have another observer who's controlling the controllers, who's going in and saying, oh, you know what, show this one, oh, show that one. And we have an extra navigational, that's just one example. We have navigation that we can stick inside of views, observers that say, hey, when the user clicks on this picture, open up this view over here. And it's basically the guy who's sitting in between all the different views and all the different controllers, and he's like the traffic cop. He's observing what's going on and orchestrating and updating everybody and changing everything, which is that third, it's the fourth component that kind of fits in there for flexibility in terms of the design pattern. That kind of makes it all work, and he's responsible for making it all work. So, observers rock. So, responsible. Observer pattern allows, if you're going to use an observer pattern, Model-View-Controller doesn't always have to use an observer pattern. The observer pattern, if you're doing the tab application template actually gives that to you. So here's the thing with the templates. We have single view template. Now I'm talking a lot about iPhone because you guys are using Objective-C for iPhone, and some of you are taking both classes, or who programs for the Mac? Everybody learns Objective-C to program for the iPhone or for iPads or iOS devices, especially when it's the same thing. But anyway, long story short, you go in and you got this template and that template and this. Those are design templates, by the way. The tab controller has an observer in it already for you, so you don't have to make one. The single view one has a view controller and a single view one. You can turn on or off the storyboard. Storyboard has an observer in it. It has a storyboard controller that has a bunch of views in there, and you're modifying. And the best thing to do is just to, just play around. You can actually go from one button, from one view to another view without using any of the controllers. You're using the observer is working for that. The observer is actually making that happen. In fact, I'm going to show you real quick because a lot of people, when I get done with this lecture. Well, it's 6:20? All right, so let's, I only have a couple slides left here, so I won't show you the game thing. I'll show you what I'm talking about in terms of the observer in a few minutes. But here, so this is the architectural diagram where we have the business logic here and the model. It's going to do the update. It's going to update the view. It's going to get the state of the view from the model representation. The controller is going to work with the model. It also works with the view because it controls the user's actions that are happening from the view. It controls the changes that are happening in the data. They're all sort of working together. All of these different components are working together. Advantages: separation between the data layer and the interface is key. Key for abstraction, for making it easier to understand but easier to update, and it lends itself to a better built application. So the view is the easily replaced and expandable. So you take the data model and you get a new device and you just build it for the new device. So that's how you can create multi-purpose devices in the new iOS. It works on iPad, it works on iPhone. It's just the whole model is the same, the controllers are the same. It's just the view that's different. The view is different for the different device. So a new device comes out, and just write a new view for it. Makes it extendable, makes it reusable. Model data changes are reflected in all of the interfaces because all of the views are observers. All the views have an observer component in them. Okay, so in Android or in other environments, they call them action listeners. They call them, observers are like action listeners, touch controllers, in terms of the interface for the view. Better scalable, since the UI and the logic application are separated and distributed over a network, is greatly simplified. Yes, because you just put the network, you just put all of the views out there and all of the data is on the server side. So definitely works out better. Problems associated with this? Problems of translation. Business logic blends into the controllers. Yeah, it's kind of like, it's hard to know what belongs where. What's part of the controller, what's part of the business logic. And most people have a tendency just to stick it in the controller. So the view controllers are stacked full of functionality, normally. Nobody wants to create an extra object for it or store it, actually anything else anywhere else, because it's easier just to stick it in the view controller. And problems of the pattern: excessive coupling between the model and the view and the model and the controller. Excessive coupling. There's too much communication going on. They require too much interaction with each other. So it could run a little bit slower depending upon how you've built the application. If it's a huge one, you're not going to get a huge one on an iOS device that's going to ever show a problem. But maybe on a MacBook, maybe if you're writing a huge word processing program or something, it might run a little slower because of the coupling that's going on. You want to reduce the amount of coupling. This creates an excessive level of coupling between the components. And then frozen interfaces are hard to manage. Yeah, what froze the interface? Finding a bug in that is ridiculous. Let me show you what I mean, and I'll just bring it up real quick, and I'll just create a new project here. It just takes a second, actually. I'm going to create a project with a storyboard. I'm going to call it test. I'll do a single view, and I'll do a storyboard. I'm going to call it, yeah, it doesn't really matter what I call it. Because most of you guys know the basic parts of this already, so I can demonstrate what I'm talking about real easily. If I have a storyboard out here, and I just clicked on it and I'm waiting for it to load, I see my little spiral wheel is going around thinking. I have this view controller out here, and I pull out another view controller and I stick it out here. And I put a button out here as an example. Oops. Hey, come on. I confused it. Now let's put the button over here. And I control drag the button over to this view. And I say it's a modal, which means load it up in the same space that the previous view was in. And then click me. I haven't used any view controllers at all. I could, if I wanted to, come over here as an example and create an interaction with the view controller, and this would be the interaction I'd go. I'd say, you know, oh, touch up inside, control drag over here, and say button touched, button tapped. Change it to a button type. And then over here, I've got the link created. But I don't need this if I have an observer, which I have in this application. And I know I have an observer because watch this. There's no code written to switch between the two, but the observer is going to know that my one screen that I controlled through that button, and I dragged it over to the other view, the views are now connected. The views are now going to essentially, from the observer level, not from the code, I didn't write any source code. But if I do this, well, you can't tell, but I should have put a label on it. But the other view is now showing. There's no code for that. It's I took advantage of the observer. So if you know the observer is there, you can use it. Same thing as with, if for example, the tab view. If I have time here. Let me just bring it real quick. Show you another kind of concept of the observer. The tabbed application comes with a default template for that. I'm going to say just example tab. Example tabs. There we go. It doesn't matter if I use the storyboard or not, actually. If I bring this up, I'm going to automatically, and this is right here, this is my observer. My observer is going to switch between the two. So if I, actually it's already set for me, which is great because people couldn't figure out what does this world does this design template do. So the code is actually written for you already on here. If I go first view and I click here, I got second view, first view, second view. This is the observer component who's sitting out here as the tab controller, who's switching between the two different views. These are the views, these are the windows. Each one of these views has a first view controller, and the other one has a second view controller over here. These controllers are where you're supposed to put the logic for when people click on the views. The other logic for controlling between the views, the navigation between the views, goes with the tab bar controller. I keep calling it a view, it's really called the tab bar controller. And we have one, two, three different components represented here. And then put the data in there. Where's the data going to go? The data's going to go right here. Or the data's going to go in a class that you're going to create that's going to drive your application data. So anyway, that was the objective of today's lecture, was to kind of make this kind of a little bit more obvious in terms of the design pattern. If I go, actually here, let me show you something real quick actually. We have the same thing. If we go into a non-iPhone application, I'm going to close this simulator. We don't need the simulator anymore. And I create a project here, and instead of going for an iPhone application, I go for a Coca application. I click this one down here, Mac, and I go for Coca application over here. And I click next, and I type in Coca instead. And let's see, core data use. Okay, that's good. What did that say? Hopefully I created the window-based application. I may not have used the right template, but let's see. So we have the app delegate, and I still have the main window. So I have the view and the data, but I don't really have, the controller is actually mixed. So let's see. I should get a blank window that shows up actually by default because I have a main view. And yep, here's my main view. Same concept. This is the view, and the data that's associated with it. We don't have a controller, however. Instead, we have components for menus. So we have a font manager, menu manager, menu, like for example, here let me run it again so you see what I'm talking about. Actually, it's still running. Oops. No, here it is. If I click on this, you see up here on the top, it is still running in the back. I have two instances of it gone. I have the menu component up here on the top. It's not programmed or anything, but I could add items to the menu. And we could write Notepad in here really easily, actually. The GUI control is the same, because if I go over here and I type over here, I can go on push button. It's the format for creating the app is almost identical. So it's just a matter, and the model view controller is identical. So if I had some stuff here in this view, I created a single windowed application. Didn't see that many. I didn't see actually that many templates. I believe there are packages that you can actually install for more templates for different types of applications. But long story short, I could go in here and say view and pull out a image well, a text view, actually a GI, OpenGL view. I think I can actually do a UI view in here. Nope. I don't have the library correct. But in my object library, I can go data views, controls. So data views, let's try data views here. A table view, I can pull a table view out, put it in here. Take the multiple views, switch the window to store the different views, and then if that were the case, I'm gonna use a controller. So I'm gonna have controls that are gonna essentially navigate between the views. I could actually create a view controller as well, you know, just by coming up and going, you know, file, and then creating a view, creating a window, creating a controller for it, or storyboard, stuff like that. So, all right. So next time will be different topics, moving on to different, bigger and better things, and I'll see you next week.